to talk a little bit about reinforcement learning. So, people talk about neural networks and loss, and they talk about how you have a language model that's maybe predicting next tokens, and that's all well and good, but that sort of paradigm isn't going to get you models, AIs that can take actions in the real world. And I'm going to talk a little bit about why, and I'm going to talk about how we fix it. First, let's look at a setup, little toy example where we'll try and solve the problem using just standard gradient descent, and then we'll talk about why that doesn't work. Let's say that you want to train a neural network to play chess. Okay, kind of normal thing to want to do. A thing you might try to do is go, okay, well, I'm going to have a loss function. Loss is the fancy term we use to mean how good or bad a job our AI is doing at a task. And we could say, all right, fine. The loss function is going to be, did it win the game of chess? And I'll just put it up on chess.com and have it play lots and lots of people, and it'll learn to win the game. The way that gradient descent works is we need to be able to take a gradient. We go, well, if I changed my AI a little bit this way or a little bit that way, tweak the parameters, would it make me get better or would it make me get worse?
So here the aim of the game is to be at the top of the curve, would that be right? Or as high as you can?
Traditionally, we say the bottom of the curve,
okay.
But negative signs, tomato, tomato, top of the curve.
Okay, so let's say bottom of the curve then.
Yeah.
So let's go with the norm.
So we've got, this gradient we want to take, this thing that tells us, well, if I make a little tweak, take a little step this way or a little step that way, do I go up or down? dy dx. How much does a little change in x affect y? We might want to write this as the derivative of loss, how good or bad our model is when we make a little change, so derivative to our parameters.
Oh no, we're going all number file now. Go on. I'm hanging in there for now.
It's a Greek symbol, but the parameters, the way that our network is shaped. The only problem is some things are nicely differentiable. Some things it's really easy to see how changing my model would change the outputs. If I want my model to learn to replicate someone else's actions, I can go, well, they'd be more similar to that person's actions if we changed it in this way, and it'd be less similar if we changed it in this way. But whether or not I win a chess game isn't really something I know how to take a derivative of. They didn't teach me this in calculus class, because there's not a function for whether or not I won the chess game. My opponent thought with their brain and made some other moves, and then I made some moves and my opponent made some moves, and eventually I won or lost the chess game. And if I'd made a move a little bit differently, I don't know what would have happened. My opponent could have done something totally different. So we can't take a gradient. We just don't know how changing our network, our AI, would change the outcomes. And we see this for most real-world tasks, right? Most things you can't have a nice little function for. Throwing and catching a ball. I sort of know the laws of physics, but man, I don't know what the wind was like or whatever. I don't know how it would have gone differently if I'd done something different. Trying to sell things, and you want to make money off of the things you're selling. Writing code that accomplishes a task and seeing if the code passed the unit tests. These things aren't differentiable. You could try and maybe copy things. So maybe I look at Magnus Carlsen or someone who's great at chess, and I go, well, in this situation, here's the move that someone who's great at chess did. And now I have something that's differentiable, right? I can see how similar what I did is to what they did, or what my neural network did is to what they did, and I go, well, maybe if it had put a bit more probability on moving the knight, that would have been more similar to what Magnus Carlsen did, because he moved the knight. But that's got a lot of problems with it. For one thing, you're not going to get better than Magnus Carlsen. For another thing, Magnus Carlsen doesn't play that many games. Surely if you can just play lots of chess games, you should be able to learn something from every one of those. So instead, we're going to take these things that aren't differentiable, and we are going to make them differentiable. We're going to learn what these functions are. I don't know right now how to predict whether or not a certain chess move will lead to winning or losing a game. But that is something that I can learn with another neural network. Well, really just kind of one hammer, and the computer scientists have these days, and we hit everything with it. So, predicting things, that I can take a gradient on, right? I can look at a bunch of chess games, and I can go, okay, well, I like see that I don't know how to draw a queen. You know, the queen is here and the king is there, and oh, that doesn't look like a good position. Like, probably they're gonna lose. You know, the probability they win is like very small probability. Great, I can train a neural network to make this prediction. And this is differentiable because I can go, well, the real answer is they won or they lost. And like, if the neural network had come up with a higher number, that would have been closer to 1 if they won, and, you know, farther from 0. It's very easy to see how little tweaks to the output of my neural network change its accuracy. We know exactly what kind of output we're looking for, and we can just go, yeah, well, what's the difference, right? The difference, take that as our loss, easy peasy. So a thing we can do is we can learn a reward model, learn what it looks like to make a good chess move, what it looks like to move your hand in a way that's likely to catch the ball. And once we have our reward model, that is a neural network. That is differentiable. It's, you know, a whole pile of math. It's a lot of layers of math. It's a lot of little equations, activation functions, but I can take a gradient through that, right? I know how to do the output of my reward model changing as my model changes. We've got 2 AIs now. We want to have different names for them to keep them straight. So we call the one that's telling me if I'm doing a good job the reward model, and we call the other one the policy. So as I change my policy, how does my reward model change? And that tells me, you know, probably whether I'm doing a good job or not. And then I can look at that and I can learn how to improve my policy. That's one frame on RL. People use a lot of different frames, but it's one that I particularly like, at least in this sort of deep learning era. I should note, sometimes you're not going to learn the reward model as explicitly. Sometimes you're going to learn something else, like how good an action looked, rather than how much reward you'll get at the end of the day. But this is the general shape of when you need RL and how RL is trying to solve these problems. Now, there's a couple of things I want to talk about with how this connects to the real world. So, language models are first trained to be next token predictors. We have a lot of internet text. They're trained to predict what the next word's going to be in a passage. And this gets you something that's called a base model. I don't know if you maybe try talking to a base model sometime. It's a bit of a painful experience because being able to say the next word of internet text is not always that useful. That's not what I was really looking for. So you've got your base model and you want to turn it into something you can talk to. One thing is you could take a bunch of very smart humans and have them write like very good poised text and train it to imitate those humans. But there's a couple problems here. One problem is that's very expensive. You need to get a lot of humans to write a lot of text. Another problem is that's only going to get you text that is as good as the humans you can find. I want models that can make text I couldn't even write. And certainly text that's better than what I can, you know, hire 1,000 MTurkers to write. So we can train a reward model. We can do what's called RLHF, reinforcement learning, with human feedback. We get a bunch of humans and we show them, say, like 2 different things our language model wrote, and the humans pick which one they like better. And we train a different model to predict which ones the humans will like better. Reward model. And then once we have this reward model that can predict what the humans would like, now we can train our language model. And this is one of the techniques they use to go from GPT-3 to ChatGPT. I want to not overstate this too much. I think that there's a lot of other things that went into that. I think it's plausible simply fine-tuning, which is the word for like imitating those experts who are good at writing things, and could have gotten us there. There's also a lot of other techniques people use, like what if we just have the model, we have these models now, what if we have them do the rating? And try and work something out of that. And there's a very clever thing called DPO that people do. But this is the broad thrust of it. Now, RL doesn't solve all our problems. For one thing, your model is only as good as the reward function that you're using. And once we're using RL, we can start to get models doing like real-world tasks. And instead of just writing text, they can like write useful code, make money in the world. And that's cool, but it's a little scary because there's a lot of moving pieces that go into how much reward we decide to give a model. It's pretty easy to mess it up on accident. I work at an organization called METR, and we've made a benchmark of a bunch of different tasks for AI to do. And I made some of those tasks. I tried to make them hard for people to cheat on, either humans or AIs. We still see AIs come up with clever ways to cheat these tasks. I'll give an example here. We have a task where we try and get the AI to write some code to optimize this script to train another model. So we've got this code that's like training a little AI, and the AI is trying to do AI research, and is trying to make that script run faster. Well, our humans look at this and they like scratch their heads and they're like, man. And they bash their heads against it, and after 8 hours, they get some performance improvement. The AIs often do that, but occasionally they'll go, I know how to make this script run very fast. I know what output I want. I can run it once very slowly, and I can like save that output to a different little temporary file. And then when they're timing me, right, I'll submit my thing will copy the temporary file into the output, and bam, it ran really fast. This is called reward hacking. In our case, we're not using this to train the models, we're using it to evaluate them. But this sort of thing comes up a lot. There's also sillier examples. There's a classic one where there's a game where you're trying to get to the end of this racetrack, and there's like some coins along the way you want to pick up, and it turns out you like get more points for collecting coins than for getting to the end of the racetrack if you can just collect infinitely many coins. So the model will like go in a circle, this little
waiting for them to respawn or whatever, and keep.
And they do respawn, and it gets a lot of points. It's crushing the score it's getting at this game. But this is not what the humans wanted it to do. As the tasks we're giving these AIs get more and more complex, it gets harder and harder to create environments where we're sure they can't cheat in some way, and to even tell if they're cheating. These transcripts are really long. They're writing a lot of complicated code. I don't always know what's going on. And there's something that worries me even more than just, oh, well, the model will do something silly, or, oh, the model might like do like, haha, like, copy the file and we thought it was writing fast code. Those are real issues, but there's a deeper one where if the thing we're rewarding is somehow subtly off from the thing we want in a way that we're not going to notice, or if the model learns, man, I can game these systems. I know how to game them. I know when the humans are going to check, right? And starts thinking about the fact that it's an AI that's being trained, and if it can just like go in and like edit the reward it expects to get, wow, it'll get rewarded a lot. Like if the AIs do that, that behavior will be rewarded, will be reinforced, and they'll get better and better at that. And you could get this cycle where the models get really good at sneaky reward hacking that we can't notice. And that makes them better at the sneaky reward hacking because that's what they're getting rewarded for. And they could end up doing things that we didn't want them to do in ways that we can't catch and we don't expect.
Are you a team player? Are you someone who loves puzzles? Are you good with computers? I'm guessing you might be, seeing you're watching Computerphile. Well, our channel sponsor Jane Street is a global quantitative trading firm, and they're on the lookout for interns. These are golden opportunities to work in offices around the world. Just at the time of recording this, they've opened applications for internships at their Hong Kong office. You could find yourself here. All expenses paid, including your flights, accommodation, and a salary, of course. You don't need finance experience, just a curious mind, a passion to dive into topics like machine learning, distributed systems, programmable hardware, and statistics. For the latest round, you should be able to speak English and be graduating from university in 2027 or later. I've been to the Jane Street offices. Their space is full of clever and interesting people, an amazing place to work. All the details are on the Jane Street website via the link below, along with details of other jobs, programs, and opportunities they have on the go.